Hello there and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore one of the most quietly dramatic moments in the entire history of human thought. A moment when scientists looked at something as familiar and ordinary as the warm glow of a fire, applied the most powerful mathematics the world had ever produced, and arrived at an answer so catastrophically, so completely, so absurdly wrong that it did not merely embarrass physics, it shattered it. And in the shattering, revealed something so strange about the nature of reality that even the man who discovered it spent years trying to convince himself it could not possibly be true. This is the story of the ultraviolet catastrophe. It is the story of a hollow metal box, a glowing piece of metal, two very careful physicists who did everything right and still got everything wrong, and a quietly determined German scientist who fixed the problem by breaking one of the deepest assumptions in all of classical physics. But more than anything, it is the story of a door. A door between two worlds, the smooth, continuous clockwork world that Newton and Maxwell and Boltzmann built with such patience and such genius over 3 centuries, and the strange, grainy, probabilistic world of the quantum that waited on the other side. The door opened on the 14th of December, 1900, and nothing has ever been the same since. So settle in. Let your body grow heavy and still. Let your breathing find its own slow rhythm. And allow the story of light and heat, and one of the most important wrong answers in the history of science, to carry you gently towards sleep. Towards the end of the 19th century, physics was flourishing in a way that it had perhaps never flourished before. The preceding 250 years had produced an accumulation of understanding so vast and so precise that it seemed, to many of the scientists living through it, that the great work of physics was nearly complete. The fundamental laws governing the motion of objects, Newton's laws of mechanics, had stood for more than 2 centuries, tested in every conceivable situation and never found wanting. The principles of thermodynamics, developed through the middle of the 19th century, had given scientists a profound understanding of heat and energy and the way they flow and transform, and this understanding had powered the Industrial Revolution, filling the world with steam engines and factories and railways and all the material abundance of the modern age. Then there was electricity and magnetism. For much of human history, these had seemed like separate and mysterious phenomena, sparks and lightning on one hand, the invisible pull of the lodestone on the other, curiosities of nature that did not obviously fit into the grand mechanical picture of the universe. But through the first half of the 19th century, Michael Faraday had conducted a series of experiments of extraordinary insight and simplicity, demonstrating that electricity and magnetism were not separate things, but deeply, intimately related, that a changing magnetic field could generate an electric current, that electric currents created magnetic fields, that the two were aspects of something unified and fundamental. Faraday was a man of genius, but not of mathematics. He thought in pictures, in field lines, in the vivid geometric imagination of someone who could see the invisible forces threading through space as clearly as he could see the apparatus on his laboratory bench. It was left to James Clerk Maxwell to take Faraday's pictures and translate them into the language of mathematics, and in doing so, to produce one of the most beautiful and consequential achievements in the history of physics. Maxwell's equations, 4 compact mathematical statements about the behavior of electric and magnetic fields, did something that no one had anticipated. When Maxwell solved them, he found that they predicted the existence of waves, oscillating patterns of electric and magnetic field that propagated through empty space at a fixed speed. And when he calculated what that speed was, using constants that had been measured in purely electrical experiments, he found that it matched, with astonishing precision, the known speed of light. The conclusion was inescapable and extraordinary. Light was an electromagnetic wave. The warm glow of a candle, the cold shimmer of moonlight, the invisible heat radiating from a fire, all of it was the same thing. Oscillating fields, rippling through space at the speed of light, because they were light. This was, by any measure, one of the great triumphs of human intellect, and it gave physicists at the close of the 19th century a deep and justified confidence. They had electricity, magnetism, and light unified into a single framework. They had mechanics. They had thermodynamics. What remained, many believed, was simply to apply these tools, to use the known laws to explain the remaining puzzles, to calculate the remaining unknowns, to fill in the details of a picture whose broad outlines were already drawn. Let your breathing slow now. Let the weight of the day release from your shoulders. The story is long and quiet and full of wonder, and there is nothing you need to do but let it carry you. One of those remaining puzzles had to do with a question that might seem, on its surface, almost too simple to be interesting. Everyone knew, from the most ordinary everyday experience, that hot objects glow. Heat a piece of iron and it begins to emit a dull red light. Heat it further and the color shifts, toward orange, toward yellow, toward a brilliant white. Cool stars glow red, hotter stars glow yellow, the hottest stars shine in blue-white brilliance. The sun, at its surface temperature of nearly 6,000 degrees Celsius, emits a warm golden light. These were facts, long known and endlessly observed. But why? What was it about the nature of matter and electromagnetic radiation that produced this particular relationship between temperature and color? The question was not merely academic. Understanding how hot objects emit light would mean understanding something fundamental about the way matter interacts with radiation, about the exchange of energy between the electromagnetic field and the atoms and molecules that make up physical objects. It was a deep question dressed in familiar clothes, and the physicists of the late 19th century knew it. To make the problem tractable, to strip it of all the specific details of composition and shape and surface texture that varied from object to object, physicists idealized it. They imagined an object that was a perfect absorber of radiation. An object that, when light of any wavelength fell upon it, absorbed that light completely, reflecting nothing, transmitting nothing. They called this an ideal black body. For obvious reasons. It would appear perfectly black, having no reflected light of its own. Such an object, by the laws of thermodynamics, would also be a perfect emitter of radiation. This follows from a deep principle of thermal equilibrium. If a perfect absorber were placed in an environment at some temperature and were not also a perfect emitter, it would absorb energy from its surroundings without radiating it back, violating the balance that thermodynamics demands. A perfect absorber must also be a perfect emitter. The black body absorbs everything and emits everything, and what it emits depends only on its temperature. Experiment confirmed this beautiful theoretical expectation. The pattern of radiation emitted by a black body, the way the intensity of emission varied with wavelength, was universal. It did not depend on whether the black body was made of iron or copper or carbon. It did not depend on the shape of the object or its surface texture. It depended only on temperature. Measure the spectrum of any true black body at any given temperature, and you would get exactly the same curve. This universality was a strong hint that the radiation was speaking to something deep and fundamental about the relationship between matter, energy, and temperature in general. Drift a little deeper into the quiet of this night. The universe is full of such beautiful simplifications, moments where the complexity of the specific falls away and reveals the simplicity of the universal underneath. The black body was one of those moments, and it was waiting to teach physicists something they had not yet learned. To study black body radiation in the laboratory, physicists devised an elegant experimental setup. Imagine a hollow metallic box, a cube with a very small hole in one of its faces. When light from outside falls on that hole, it enters the cube and begins to bounce back and forth between the walls, reflecting again and again until it is eventually absorbed. Because the hole is very small, the probability that any given photon of light will find the hole and escape back out is vanishingly small. From the perspective of the hole, all incoming light is absorbed. The hole behaves as a black body, a perfect absorber. Now run the process in reverse. Heat the walls of the cube uniformly to some temperature. The warm walls begin to emit radiation, filling the interior of the box with a glow. The radiation bounces back and forth, reaching thermal equilibrium with the walls. And a tiny fraction of it escapes through the small hole. This escaping radiation is a sample of the thermal radiation inside the cube, and because the hole behaves as a black body, the escaping radiation has the spectral profile of a black body at that temperature. This device, the black body cavity, was the central object of experimental and theoretical investigation. Careful and painstaking experimental work, particularly by Otto Lummer and Ernst Pringsheim in the 1890s, produced precise measurements of the spectral radiance of this cavity across a wide range of temperatures. The results were beautiful curves, smooth, hump-shaped distributions that peaked at a wavelength determined by temperature and fell away on both sides. From these experimental curves, two elegant empirical laws emerged. The first was the Stefan-Boltzmann law, named for Joseph Stefan and Ludwig Boltzmann, who derived it. This law stated that the total intensity of radiation emitted by a black body, the total power per unit area summed across all wavelengths, was proportional to the fourth power of the absolute temperature. If you doubled the temperature, the total intensity increased by a factor of 16. If you tripled the temperature, the intensity increased by a factor of 81. This stark, steep relationship explained why the brightness of glowing objects increased so dramatically with temperature, and why the surface of the sun, though only perhaps twice as hot as the surface of a very hot electric heating element, is billions of times more luminous. The second law was Wien's displacement law, named for Wilhelm Wien. This law described how the wavelength at which the emission was most intense, the peak of the spectral curve, shifted with temperature. As the temperature increased, the peak moved toward shorter and shorter wavelengths. At low temperatures, the peak lay in the infrared, invisible to the eye. As temperature increased, the peak moved into the visible red, then orange, then yellow, then into the blue and violet. This was why a heated piece of iron glowed red before it glowed white. The peak of its emission was first in the red region of the spectrum, and only at higher temperatures did the peak move into the shorter wavelengths that, combined with the longer wavelengths still being emitted, produced the impression of white light. These two laws were confirmed beautifully by experiment and were deeply satisfying in their simplicity. But they were empirical laws, patterns observed in data, not derived from fundamental principles. Physicists wanted more. They wanted to know the shape of the entire spectral curve, not just its peak and its total area. They wanted to derive the full spectral radiance function from Maxwell's electromagnetism and Boltzmann's thermodynamics. And so two of the leading physicists of the age, Lord Rayleigh and Sir James Jeans, set out to do exactly that. As you rest in this quiet and growing stillness, remember that Rayleigh and Jeans were not guessing. They were not speculating wildly. They were applying the most carefully tested and most reliably successful physical theories in the world to a precisely defined mathematical problem. What they found would shake those theories to their foundations. The strategy that Rayleigh and Jeans adopted was elegant and systematic. They focused their attention on the radiation inside the black body cavity, the hollow metallic box. Their goal was to calculate the energy density of the radiation inside the box as a function of frequency, which would then allow them to determine the spectral radiance of the radiation escaping through the hole. Their approach had 3 steps. First, count the number of distinct electromagnetic standing waves that could exist inside the box. Second, determine the average energy of each of those standing waves when the system was in thermal equilibrium at temperature T third. Multiply the number of waves in each frequency range by the average energy per wave to find the total energy density in that range. The first step required understanding what kinds of electromagnetic waves could stably exist inside a metallic box. The answer came from the boundary conditions imposed by the metallic walls. The walls of a metallic box are conductors, they allow electric charges to flow freely. This means that the electric field cannot have a component parallel to the wall's surface, because if it did, the mobile charges in the metal would immediately flow to cancel it. The electromagnetic waves inside the box must therefore satisfy the condition that the electric field is zero at the walls. This is precisely the condition that gives rise to standing waves, waves that appear to stand still, oscillating in place, with fixed points called nodes where the displacement is always zero. This is the same physics that determines which notes a vibrating string can produce. A guitar string fixed at both ends can only vibrate at wavelengths for which the string's length is an exact multiple of half a wavelength. The same mathematics, applied to 3 dimensions, determined which electromagnetic waves could fit inside the box. Working through the 3-dimensional geometry carefully, considering standing waves in the x, y, and z directions simultaneously, and accounting for the fact that electromagnetic waves can oscillate in 2 independent polarization states for each direction of propagation, Rayleigh and Jeans derived an expression for the number of allowed standing waves in any given frequency range. This quantity is called the density of states. The result was clean and significant. The number of allowed electromagnetic modes in a frequency interval grew in proportion to the square of the frequency. At low frequencies, relatively few standing waves could fit inside the box. At higher frequencies, the number of available modes grew rapidly. The square of the frequency meant that doubling the frequency quadrupled the number of available standing wave modes. This growth without limit, as the frequency increased, was not yet a problem. It was simply a fact about the geometry of waves in 3-dimensional space. The problem would come in the next step. Let the image of those standing waves rest gently in your mind, not as mathematical abstractions, but as something almost physical, almost tangible. Imagine the interior of the box filled with the invisible shimmer of electromagnetic oscillations, each one fitting perfectly between the walls, each one a distinct pattern of vibrating electric and magnetic fields. There were many of them. At high frequencies, there were very many of them. And each one, Rayleigh and Jeans were about to argue, carried the same average energy. For the second step of their calculation, determining the average energy of each standing wave, Rayleigh and Jeans turned to one of the most celebrated and well-established results in all of classical statistical mechanics. This was the equipartition theorem, and it was a theorem in the strict mathematical sense, not a hypothesis or an approximation, but a rigorous consequence of the underlying mathematics of classical statistical thermodynamics as developed by Ludwig Boltzmann and Josiah Willard Gibbs. The equipartition theorem stated something beautifully simple. When a physical system is in thermal equilibrium at temperature T, the available thermal energy is distributed on average equally among all available degrees of freedom, all the independent ways in which the system can store energy. Each degree of freedom receives, on average, an amount of energy equal to 1/2 of Boltzmann's constant multiplied by the absolute temperature. This quantity, 1/2 kT, is sometimes called the thermal quantum of energy in classical physics, though the word quantum here means simply a small amount and carries none of the revolutionary significance it would later acquire. The intuition behind the equipartition theorem is almost democratic. Thermal equilibrium is a state of maximum disorder, maximum randomness. In such a state, there is no reason for energy to prefer one mode over another, one direction of motion over another, one degree of freedom over another. So on average, each gets the same share. A gas of atoms in thermal equilibrium distributes its kinetic energy equally among motion in the x, y, and z directions. A vibrating molecule distributes its energy equally among its different modes of vibration. And electromagnetic standing waves in a cavity, Rayleigh and Jeans argued, should distribute their energy equally among all the available wave modes. For a standing electromagnetic wave, the physics is a little richer than for a simple translational degree of freedom. A standing wave oscillates sinusoidally in time. It is, in effect, a harmonic oscillator. And a harmonic oscillator has two kinds of energy, kinetic and potential, that alternate as the oscillation proceeds. For such a system, the equipartition theorem gives an average kinetic energy of 1/2 kT and an average potential energy of 1/2 kT, for a total average energy of kT. Each standing wave in the cavity, regardless of its frequency, regardless of its wavelength, regardless of any other property, should carry on average exactly kT of energy. This was not an approximation. It was not a rough estimate. It was what the mathematics of classical statistical mechanics unambiguously and rigorously predicted. Rayleigh and Jeans had every reason in the world to trust it. The equipartition theorem had been verified in gases, in solids, in liquids, in a wide variety of physical situations. There was no evidence that it failed. There was no reason to doubt it. And so they combined their two results: the number of standing wave modes in a frequency interval growing as the square of the frequency, the average energy per mode equal to kT, constant across all frequencies. Multiply them together and you get the energy density of the radiation inside the cavity as a function of frequency. This was the Rayleigh-Jeans law, and when they plotted it against the experimental curves, the result was a disaster. Let the quiet of this night hold you gently as the story reaches its most dramatic moment. There is something almost poignant about what Rayleigh and Jeans found, not because they made an error, not because they were careless, but because they did everything right, followed every rule that physics had given them, and arrived at a conclusion that was completely, obviously, catastrophically wrong. The Rayleigh-Jeans formula predicted that the energy density of blackbody radiation should increase without limit as the frequency increased. At low frequencies, long wavelengths, in the infrared region of the spectrum, the formula agreed reasonably well with the experimental data. The curve matched the measurements in that region. But as the frequency increased, moving through the visible spectrum toward the ultraviolet and beyond, the Rayleigh-Jeans curve diverged wildly from the experimental results. Where the experimental curves peaked and then fell gracefully away to zero, the Rayleigh-Jeans formula kept climbing, steeply and without bound, racing upward toward infinity. The physical meaning of this prediction was staggering. According to the Rayleigh-Jeans law, any object at any temperature above absolute zero should be radiating an infinite amount of energy at very high frequencies. Not a large amount. Not an unreasonably large amount. Infinite. The mathematics said that the total energy contained in the radiation inside any blackbody cavity, the integral of the energy density over all frequencies, was infinite. Every warm object in the universe should be a source of infinite energy, pouring out an unbounded flood of ultraviolet light, X-rays, gamma rays, and every higher frequency radiation without limit. It is almost impossible to convey how wrong this is. Not merely quantitatively wrong, in the way that an approximate formula might give an answer that is off by a factor of 2 or 10. Qualitatively, fundamentally, completely wrong. The world does not work this way. A warm cup of tea does not emit infinite energy. A piece of iron heated to a dull red glow does not destroy its surroundings with a torrent of X-ray radiation. The sun does not emit infinite ultraviolet light. None of this happens, and everyone knows it does not happen, and the equations of classical physics were predicting that it should. Because the divergence occurred at high frequencies, at the ultraviolet end of the spectrum and beyond, the problem became known as the ultraviolet catastrophe. It was a catastrophe in the truest sense of the word. Not merely a failure of one formula or one approximation, but a demonstration that the most fundamental tools of classical physics, Maxwell's electromagnetism and Boltzmann's thermodynamics, were in some deep and not yet understood way inadequate. They could not describe even the most commonplace phenomenon of everyday experience, the warm glow of a heated object, without predicting an infinite energy output. Rayleigh and Jeans had not made a mistake. The mathematics was correct. The application of the equipartition theorem was correct. The counting of the standing wave modes was correct. The problem was not in the execution. The problem was in the foundations. Something that classical physics assumed to be true, something so basic that it had never been seriously questioned, was wrong. As you drift deeper into the warmth and stillness of this night, consider what it means to discover that a foundational assumption is wrong. Not a peripheral detail, not a minor approximation, something central. Something that the entire framework depends upon. It is a terrifying and exhilarating discovery, and it demands a response that is not merely technical but conceptual, a new way of thinking about the thing that was assumed. Into this crisis stepped Max Planck. He was not, by temperament, a revolutionary. He was born in Kiel, Germany, in 1858, into a family of scholars and lawyers, and he carried with him throughout his life a certain conservative dignity, a preference for order and tradition, a deep respect for the edifice of physics that his predecessors had built. He had devoted his career to thermodynamics, to the study of heat and energy and entropy, and he was deeply, personally invested in the coherence and completeness of the classical framework. When the ultraviolet catastrophe emerged as a problem in the 1890s, Planck did not approach it as someone eager to overthrow the old order. He approached it as someone who believed deeply that the old order could be saved. He began by focusing on the experimental data. The experimental curves for black body radiation were, by the late 1890s, known with considerable precision, thanks to the careful work of Lummer and Pringsheim and others. These curves had a very specific shape. They rose from zero at long wavelengths, peaked at a wavelength determined by the temperature, and then fell back towards zero at short wavelengths. Planck studied these curves carefully, comparing them with what theory predicted and looking for patterns. He noticed something important. At long wavelengths, low frequencies, the experimental data agreed with the Rayleigh-Jeans formula reasonably well. This suggested that the equipartition result of kT per mode was approximately correct in that regime. At short wavelengths, high frequencies, the experimental data showed the energy density falling steeply towards zero, while the Rayleigh-Jeans formula predicted it rising to infinity. Whatever the correct formula was, it had to reduce to the Rayleigh-Jeans result at long wavelengths and go to zero at short wavelengths. Planck spent months, and then years, wrestling with this problem. He tried interpolating between known limiting cases, searching for a function that would fit the experimental curves across all wavelengths. In October of 1900, he found one, a mathematical formula that matched the experimental data with extraordinary precision. He presented this formula to the German Physical Society on the 19th of October, 1900, and it was received with great interest. But a formula, however accurate, is not a physical theory. Planck knew that he needed to understand why his formula worked, what physical principle it was encoding. Over the following weeks, working with what he later described as an intensity born of desperation, Planck found the answer. And the answer required him to abandon one of the most deeply held assumptions in classical physics, the assumption that energy was a continuous quantity. Let your mind grow quiet and still as we approach this moment. It is one of the most remarkable intellectual acts in the history of science. A man doing something he did not want to do, taking a step he did not want to take, because the universe was insisting, and he was too honest and too rigorous to look away. The key to understanding Planck's solution lies in returning to the average energy calculation, the step where the equipartition theorem had assigned kT of energy to every standing wave mode, regardless of frequency. This was the step that produced the ultraviolet catastrophe. If the average energy per mode were the same at all frequencies, kT, constant, flat, then multiplying by the rapidly growing number of modes would inevitably produce an energy density that diverged at high frequencies. What if the average energy were not constant? What if, at high frequencies, the average energy per mode were much smaller than kT, so much smaller that the declining energy per mode more than compensated for the growing number of modes, causing the total energy density to peak and then fall. This was what the experimental data were clearly showing. The energy density did peak and fall. The average energy per mode must be smaller at high frequencies than at low ones. But why would this be? What physical mechanism could cause the high-frequency modes to have less average energy than the low-frequency modes? The equipartition theorem was unambiguous. It said that each mode should have the same average energy, kT, in thermal equilibrium. If the high-frequency modes were getting less, it meant the equipartition theorem was failing. But the equipartition theorem was not a guess. It was a theorem, derived rigorously from the principles of classical statistical mechanics. How could a theorem fail? Planck found the answer by going back to the derivation of the average energy. The classical derivation used the Boltzmann distribution, the probability distribution over energies that classical statistical mechanics predicted for a system in thermal equilibrium. In the classical case, the energy of each mode was assumed to be a continuous variable. It could take any value from 0 to infinity, varying smoothly and without restriction. With this assumption, the average energy worked out to exactly kT, as the equipartition theorem required. But Planck asked, what if the energy were not continuous? What if each electromagnetic standing wave mode could only possess energy in discrete amounts, in multiples of some basic unit? What if you could not have half a unit, or a quarter of a unit, or any fractional amount, only whole number multiples of the basic unit? This was the hypothesis of energy quantization. Planck proposed that the energy of a standing electromagnetic wave of frequency f could only take values that were integer multiples of a basic energy unit, which he wrote as hf, where h was a new fundamental constant of nature that he introduced. This constant is now known as Planck's constant, and it is one of the most important numbers in all of physics. Its value is extraordinarily small, approximately 6.6 times 10 to the minus 34 joule-seconds, which is why the discrete, quantized nature of energy is invisible in everyday life. With this assumption in place, Planck recalculated the average energy of an electromagnetic standing wave in thermal equilibrium. The calculation was similar to the classical one, but with a crucial difference. Instead of integrating over all possible energies from 0 to infinity, the sum ran over discrete values, 0, hf, 2hf, 3hf, and so on. The mathematics of this discrete sum was different from the classical integral, and it produced a profoundly different result for the average energy. At low frequencies, where hf is much smaller than the typical thermal energy kT, the quantum result reduced smoothly to the classical result of kT. The discreteness of the energy levels was so fine, compared to the available thermal energy, that the system behaved as if the energy were continuous. This explained why the Rayleigh-Jeans formula worked at long wavelengths. In that regime, the classical and quantum results agreed. At high frequencies, where hf became comparable to or larger than kT, the quantum result diverged dramatically from the classical one. The average energy per mode no longer stayed at kT. Instead, it fell steeply. The high-frequency modes were effectively frozen out, unable to be excited because the minimum energy they could hold was too large compared to the available thermal energy. A mode with energy quantum hf much larger than kT could receive that energy only rarely, through a statistical fluctuation of sufficient size, and most of the time it would simply sit with zero energy, contributing nothing to the total. This was the mechanism that the data had been demanding. High-frequency modes could not be continuously excited by infinitesimal amounts of energy. They required a minimum payment of hf, and if that minimum was too large, they simply went unoccupied. The ultraviolet catastrophe was avoided not by changing the number of available modes, but by removing their ability to hold energy in arbitrarily small amounts. When Planck combined his new average energy formula with the density of states that Rayleigh and Jeans had correctly calculated, he obtained a new formula for the spectral radiance of a black body. This formula is now known as Planck's law, and it is one of the most important equations in all of physics. When plotted, it produced curves that matched the experimental data with extraordinary precision, not approximately, not in some limiting case, but exactly across the full range of wavelengths at every temperature that had been measured. The smooth, hump-shaped curves of the experimental data, which had resisted theoretical explanation for decades, fell perfectly onto the theoretical curves that Planck's formula predicted. Furthermore, Planck's formula had the right limiting behaviors. At long wavelengths, it reduced to the Rayleigh-Jeans law, confirming that the classical result was correct in that regime. At short wavelengths, it predicted the rapid fall-off to zero that the experiments had shown, and that the Rayleigh-Jeans formula had so catastrophically failed to reproduce. Wien's displacement law, the empirical observation that the peak wavelength shifted inversely with temperature, emerged naturally from Planck's formula as a mathematical consequence, not an independent assumption. And the Stefan-Boltzmann law, the proportionality of total emitted power to the fourth power of temperature, also followed directly. Planck presented this complete theoretical framework in his famous lecture on the 14th of December, 1900. He was 42 years old, at the height of his intellectual powers, and he understood that what he had done was significant, but he may not have fully understood how significant. He had introduced a new fundamental constant of nature, his constant h, and had proposed that energy was quantized, but he hoped, in the months and years that followed, that this quantization was somehow a property of the interaction between matter and radiation, a mathematical device rather than a fundamental truth about the nature of energy itself. He hoped that someone would find a way to derive his formula from classical physics without the need for energy quantization. No one did, and as the years passed, it became increasingly clear that the quantization was real, not a trick, not a device, but a genuine feature of the physical world. Drift deeper now, as the story expands outward from this single discovery into the vast landscape it made possible. The 14th of December, 1900, was not merely the day a formula was corrected. It was the day a new physics was born, though no one in that lecture hall in Berlin could yet see the full dimensions of what was beginning. Planck himself struggled for years with the implications of his own discovery. He had introduced the quantum of energy, the idea that HF was a minimum, indivisible unit of energy for electromagnetic radiation of frequency F, but he had done so as a mathematical hypothesis, a formal trick to make the calculation work. He was not convinced, and did not want to be convinced, that this quantization represented a fundamental truth about nature. It was Albert Einstein who took the next decisive step. In 1905, the same miraculous year in which he published his papers on special relativity and Brownian motion, Einstein proposed that Planck's energy quantization was not merely a property of how matter exchanged energy with radiation, but a fundamental property of radiation itself. Light, Einstein argued, was not merely a wave in the way Maxwell had described. It was also, in some deep sense, a collection of discrete packets of energy, what we now call photons. Each photon carried energy equal to hf, where f was the frequency of the light. Einstein used this hypothesis to explain the photoelectric effect, a phenomenon in which light hitting a metal surface could eject electrons from the surface, but only if the light had a frequency above a certain threshold, regardless of how intense the light was. This was inexplicable on the wave picture of light, but followed immediately from the photon picture. Each photon had to have enough energy to liberate a single electron. Low-frequency photons, however numerous, each had too little energy. High-frequency photons, even if few, each had enough. The threshold frequency corresponded to the minimum energy needed to eject an electron. This explanation was elegant and compelling, and it was confirmed by careful experiment. Einstein received the Nobel Prize in Physics for this work in 1921, not for relativity, but for the photoelectric effect and the photon hypothesis. The photon was the first quantum particle. It was the first demonstration that the discreteness Planck had introduced was not a property of matter's interaction with radiation, but a property of radiation itself. Light came in chunks. Energy came in chunks. The smooth, continuous world of classical physics was, at the level of individual quanta, actually grainy, made of discrete, indivisible units too small to see individually, but real and fundamental nonetheless. As you rest here in the soft dark of this night, consider what an extraordinary shift this represented. For centuries, the physical world had been understood as smooth and continuous, a world in which you could always find something halfway between any 2 points, a world in which energy could be divided arbitrarily finely without limit. The quantum revealed that this smoothness was an illusion, or rather, an approximation, accurate at the scales we could see and measure in everyday life, but breaking down when you looked closely enough. The world was, at its deepest level, made of pieces. The implications of Planck's discovery unfolded slowly at first, then with gathering speed, until they had transformed not just physics, but the entire technological and material landscape of human civilization. 13 years after Planck's lecture, in 1913, a young Danish physicist named Niels Bohr used the idea of energy quantization to solve another long-standing puzzle, the structure of the atom. Atoms, it had recently been established, consisted of a tiny, dense, positively charged nucleus surrounded by negatively charged electrons. But classical physics predicted that such electrons, being accelerated charges, should radiate electromagnetic energy continuously, spiraling inward and crashing into the nucleus in a tiny fraction of a second. Atoms, according to classical physics, should not be stable, but they were. You are made of them. Everything is made of them. Their stability was one of the most basic facts of existence, and classical physics could not explain it. Bohr proposed that electrons in an atom were restricted to certain discrete orbits, quantized energy levels, and that an electron in one of these allowed orbits did not radiate energy, despite being an accelerating charge. Only when an electron jumped from one orbit to another did it emit or absorb energy, doing so in a discrete packet, a photon, whose energy was exactly equal to the difference in energy between the two levels. This explained not only the stability of atoms, but also the sharp spectral lines, the specific, precise wavelengths of light that atoms emitted and absorbed. These spectral lines had been observed and catalogued for decades, but their origin had been completely mysterious. Bohr's model, built directly on Planck's energy quantization, explained them perfectly for hydrogen, the simplest atom. Bohr's model was not the final answer. It worked beautifully for hydrogen, but could not be extended straightforwardly to more complex atoms. The full quantum mechanical description of the atom required the development, through the 1920s, of a deeper and more comprehensive framework, quantum mechanics, through the work of Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and many others. But the seeds of all of it lay in that hollow metallic box, in those experimental curves, in the act of desperation that Max Planck described when he looked back at those years. Quantum mechanics, once developed, explained the periodic table of the elements, the fact that elements with similar chemical properties recurred at regular intervals, something that had been known since Mendeleev's work in the 1860s, but had never been truly understood. It explained the nature of chemical bonds, and therefore the structure of molecules, and therefore the behavior of materials, why some substances conduct electricity and others insulate, why metals are shiny, why diamonds are hard, why DNA has the structure it does. It explained the behavior of semiconductors, which led to the transistor, invented in 1947. The transistor led to the integrated circuit, which led to the microprocessor, which led to the computer, which led to the digital network of information and communication that now connects every corner of human civilization. The laser, one of the most transformative technologies of the 20th century, used in everything from surgery to telecommunications to barcode readers to DVD players, operates on quantum mechanical principles that trace directly to the understanding of how atoms emit and absorb photons. Medical imaging technologies, including MRI, are grounded in quantum mechanics. Solar panels convert light into electricity through the photoelectric effect, Einstein's quantum explanation, Planck's quantum foundation. The global positioning system uses atomic clocks whose precision depends on quantum mechanical transitions in atoms. All of it. Every digital device, every laser, every MRI machine, every solar panel, every atomic clock, all of it traces its lineage back to that smooth experimental curve in the laboratory of Lummer and Pringsheim, and the catastrophic failure of the formula that Rayleigh and Jeans derived from the best physics in the world. Let the immensity of that cascade of consequences settle gently around you as you sink deeper into rest, from a hollow metal box to the digital world. From a curve that would not fit to the transistor and the laser and the MRI. It is one of the most remarkable chains of consequence in human history, and it began with a wrong answer. There is a particular quality to the late 19th century that is worth pausing to appreciate before we move deeper into the story. It was an age of almost boundless scientific confidence, not arrogance exactly, but a settled certainty that the great questions were being answered, one by one, and that the pace of answering was only increasing. The tools were sharp, the methods were proven, the community of scientists was larger and better organized and better connected than it had ever been. Journals carried results across continents within weeks. International conferences brought the leading minds of the age into the same rooms, where they could argue and compare and build on each other's work. And the results of all this effort were extraordinary. The periodic table of the elements, assembled by Dmitri Mendeleev in 1869, had brought order to chemistry, showing that the elements, arranged by atomic weight, fell into repeating patterns of chemical behavior, with elements in the same column sharing properties as reliably as siblings sharing features. The atomic theory of matter, the idea that all substances were made of discrete, indivisible atoms, was gaining acceptance, though it would not be firmly established until the early 20th century. The laws of thermodynamics had been developed into a comprehensive framework by Rudolf Clausius, William Thomson, and Ludwig Boltzmann, giving scientists a deep understanding of heat, work, energy, and entropy. And Maxwell's electromagnetic theory, completed in the 1860s, stood as the supreme achievement of the classical period, a theory of breathtaking scope and elegance that unified phenomena that had seemed utterly distinct and revealed the electromagnetic nature of light. It was natural, in this atmosphere, to feel that physics was approaching completion. Lord Kelvin, one of the giants of the age, is often quoted as having said in 1900 that there was nothing new to be discovered in physics, that future work would consist only of refining measurements to greater precision. Whether he said precisely this in precisely these words is disputed, but the sentiment was real and widely shared. The feeling was that the edifice was built. What remained was interior decoration. Then came the ultraviolet catastrophe, and with it, the dawning realization that the edifice was not nearly as complete as it had seemed, that beneath the smooth and polished surface of classical physics, something was fundamentally and profoundly wrong. As you rest in the deepening quiet of this night, let that moment of discovery settle in your imagination. The greatest physicists in the world, armed with the greatest tools their science had ever produced, looking at the glow of a heated object and finding that their tools predicted infinity, finding, in other words, that they did not understand something they thought they understood perfectly. There is a particular kind of humility that comes from that experience, and it is one of the most productive states that a scientist can inhabit. The ultraviolet catastrophe was a gift, though it did not feel like one at the time. To fully appreciate what Planck's constant means, what energy quantization actually implies about the fabric of physical reality, It helps to think carefully about what was being claimed and why it was so strange. Classical physics, in its treatment of energy, was built on a picture of continuity. A stone thrown through the air could have any kinetic energy, not just the kinetic energies corresponding to some allowed list of values, but any value whatsoever, varying smoothly as the stone moved. A pendulum swinging back and forth could have any amplitude, corresponding to any energy, and as it lost energy through friction, it would diminish smoothly and continuously from any initial energy to zero. A vibrating guitar string could in principle vibrate with any amplitude, carrying any energy. Energy, in the classical world, was like water. It could be poured out in any amount, divided into arbitrarily small portions, distributed in any way that the laws of motion and thermodynamics allowed. This picture was not merely an assumption. It was built into the mathematics of classical physics at the deepest level. Newton's equations of motion were differential equations. They described continuous change, smooth evolution, a world in which quantities varied without jumps or discontinuities. Boltzmann's statistical mechanics was built on integrals over continuous energy distributions, sums that were literally integrals, covering every possible energy value from 0 to infinity, with no gaps and no forbidden values. The continuous nature of energy was not stated as an axiom that could be questioned. It was simply how the mathematics worked, so deeply embedded that it was invisible. What Planck proposed was that this continuity was not real. At least for electromagnetic radiation, for the standing waves inside the black body cavity, the energy was not continuous. It came in chunks. You could not have half a chunk or a quarter of a chunk. You could have 0 chunks, or 1 chunk, or 2 chunks, or any whole number of chunks, but nothing in between. The size of the chunk depended on the frequency, higher frequency, larger chunk, according to the simple relation E equals hf, where h was Planck's constant. Why should this be? What physical reason could there be for energy to come in discrete packets? Planck himself did not know. He had found a mathematical prescription that worked, that produced the right answers, but he did not have a deep physical picture of why the energy was quantized. He knew that his hypothesis produced the right formula. He did not know what it meant about the nature of the physical world. That deeper understanding would come later, through the development of quantum mechanics in the 1920s. But even without that deeper understanding, the evidence was accumulating from multiple directions that quantization was not a mathematical artifact, but a physical reality. Photons were real. Energy levels in atoms were real. The discrete nature of energy was real. The universe was, at its most fundamental level, not continuous but discrete, not a smooth flow, but a counting of units. The story of the ultraviolet catastrophe is also, in a deeper sense, the story of the relationship between theory and experiment, of the way that precise measurement and careful observation can force even the most elegant and well-established theoretical framework to confront its own limitations. Otto Lummer and Ernst Pringsheim, whose experimental measurements of black-body radiation in the 1890s provided the precise data that exposed the failure of the Rayleigh-Jeans formula, were masters of experimental precision. Their work required maintaining black-body cavities at precisely controlled temperatures over extended periods, and measuring the spectral distribution of the emitted radiation across a wide range of wavelengths with instruments of high accuracy. This was painstaking work, the kind that does not make headlines, but that forms the bedrock on which theoretical progress depends. Without the precise experimental data, without curves measured carefully enough to show unambiguously that the energy density fell at short wavelengths rather than rising to infinity, there would have been no crisis to resolve. The ultraviolet catastrophe would have remained a theoretical prediction with no experimental context, perhaps noticed by some but not yet tested. It was the precision of Lummer and Pringsheim's measurements, and later the even more precise work of Heinrich Rubens and Ferdinand Kerlbaum, that made the discrepancy between theory and experiment impossible to ignore. Planck himself was deeply attentive to this experimental data. He worked backward from it, using the measured curves as a guide to the mathematical form that the correct formula should take before he had a physical justification for that form. This is a powerful and legitimate approach. Sometimes you find the equation before you understand why it is the equation, and the understanding follows. Planck found his formula in October of 1900, and in the weeks that followed worked out the physical interpretation, the energy quantization that justified it. The formula came first, the physics came after, and the physics, when it came, changed everything. This pattern, observation first, formula second, deep understanding third, is not unique to Planck. It is a recurring structure in the history of physics. The empirical gas laws of Boyle and Charles preceded the kinetic theory of gases that explained them. Kepler's empirical laws of planetary motion preceded Newton's gravitational theory that derived them. The periodic table of the elements preceded the quantum mechanical theory of the atom that explained it. Sometimes the universe shows you the pattern before it shows you the principle. The patience to collect the data carefully and the insight to recognize the pattern in the data are as important to scientific progress as the intellectual power to derive the principles from first principles. What Lummer and Pringsheim gave Planck was a pattern so precise and so unambiguous that it could not be argued away. The curves were what they were. The Rayleigh-Jeans formula was what it was. The discrepancy was real, large, and systematic, and that discrepancy demanded an explanation. There is one more dimension of this story that deserves to be told: the human dimension, the personal and emotional texture of the discovery, which is sometimes lost in the clean retrospective narratives that science textbooks provide. Max Planck, in the autumn of 1900, was not a man who expected to make a revolutionary discovery. He was a careful, methodical scientist who had spent decades working on thermodynamics, publishing papers of solid quality and significance, but nothing that would have suggested he was on the verge of something historically transformative. He was in his 40s, a professor in Berlin, a man with a family and a life, and a set of intellectual commitments that included a deep respect for the classical framework of physics. When he introduced energy quantization in his December lecture, he did not present it as a revolution. He presented it as a technical device, a formal modification of the energy calculation that happened to produce the right answer. He was explicit about this in his lecture, describing the quantization as an act of necessity rather than conviction. He genuinely hoped, in the months that followed, that someone would find a way to derive his formula without the quantization hypothesis, that the quantization would turn out to be an artifact of the way he had set up the problem rather than a fundamental property of energy. This hope was not fulfilled. And in the years that followed, as Einstein's photon hypothesis and Bohr's atomic model, and eventually the full machinery of quantum mechanics confirmed the discrete, quantized nature of energy in context after context, Planck came to accept what he had discovered, but he never became entirely comfortable with it. He was, in particular, resistant to some of the more radical implications of quantum mechanics as it developed: the irreducible randomness, the abandonment of determinism, the apparent impossibility of specifying both the position and momentum of a particle simultaneously. These aspects of the quantum world troubled him deeply, and he remained in dialogue with Einstein, who shared his discomfort for the rest of their lives. The history of science is full of such figures, men and women who opened doors they were not entirely sure they wanted to open, who made discoveries that transformed the world, but that also, in some personal and philosophical sense, unsettled them. Planck's ambivalence about his own discovery is not a weakness. It is a mark of his intellectual honesty, his willingness to acknowledge the gap between what he had found and what he had expected to find, between the world as classical physics had taught him to see it and the world as his equations were now telling him it actually was. He was, as he said, peacefully inclined. He would have preferred a peaceful resolution, a way to explain the black body curves without abandoning the continuous energy of classical physics. But the universe was not offering that option, and Planck, ultimately, was too rigorous and too honest to pretend otherwise. As you drift deeper into the comfort of sleep, let the image of Max Planck settle gently in your imagination, not the heroic revolutionary of retrospective history, but the careful, uncertain, peacefully inclined man who followed his mathematics into a revolution he had not planned and did not entirely want, because the truth was there and he could not look away from it. That, in the end, is what science asks of its practitioners. Not courage in the dramatic sense, not the courage of the battlefield or the podium, but the quieter courage of following the evidence where it leads, even when it leads somewhere unexpected, even when the unexpected place is somewhere you would not have chosen to go. The legacy of the ultraviolet catastrophe and Planck's solution extends into corners of modern life that seem utterly remote from physics lectures and hollow metal boxes. Consider the technology of photography, which in the early 20th century transitioned from chemical processes to digital ones based on electronic light detectors. The charge-coupled device, or CCD, at the heart of every digital camera converts photons of light into electrical signals through the photoelectric effect, precisely the quantum process that Einstein explained in 1905 using Planck's energy quanta. Every photograph taken with a digital camera, every image captured by a smartphone, every frame of video recorded on a modern device is the product of photons, of discrete packets of electromagnetic energy, each carrying energy HF, liberating electrons from a semiconductor surface in a process that cannot be explained without quantum mechanics. Consider the technology of solar energy. Solar cells convert sunlight into electricity through the same photoelectric mechanism. Photons striking a semiconductor material and liberating electrons that then flow as an electric current. The efficiency of a solar cell depends on the quantum mechanical properties of the semiconductor, on the discrete energy levels available to electrons in the crystalline lattice, on the size of the band gap between the valence band and the conduction band, on the probability of a photon of a given energy being absorbed and producing a free electron. None of this can be understood or optimized without quantum mechanics. The transition to renewable solar energy that the world is currently attempting is, at its technological foundation, a quantum mechanical enterprise rooted in the physics that Planck initiated. Consider medical imaging. The MRI machine that produces detailed images of the soft tissues of the human body works by detecting the quantum mechanical spin states of hydrogen nuclei in the body's water molecules. A powerful magnetic field aligns the nuclear spins, and then radio waves are used to flip them between quantum states, with the emitted radiation revealing information about the chemical environment of the nucleus and therefore about the tissue in which it is embedded. PET scanners used in oncology and neuroscience detect the gamma rays emitted when positrons, the antimatter counterparts of electrons, predicted by Paul Dirac's quantum mechanical equation, annihilate with electrons in the body. CT scanners use X-rays, whose quantum nature Einstein helped to establish. The entire apparatus of modern medical imaging is built on quantum foundations. And consider, finally, the fundamental research that continues today at the frontier of physics. The Large Hadron Collider at CERN, where protons are accelerated to nearly the speed of light and smashed together, producing showers of particles that are detected and analyzed. This machine and the theory it tests, the standard model of particle physics, are quantum mechanical through and through. The Higgs boson, detected at CERN in 2012, after decades of search, is a quantum field excitation predicted by the quantum mechanical framework. The gravitational waves, detected by LIGO in 2015, ripples in spacetime produced by the merger of black holes, were detected using laser interferometers whose sensitivity depends on quantum optical techniques. The effort to build quantum computers, machines that harness the quantum mechanical behavior of matter to perform calculations impossible for classical computers, is at the very frontier of current technology. All of it. Every thread leads back, eventually, to that hollow metal box, those smooth experimental curves, and the quiet revolution that Max Planck initiated when he allowed himself, one winter in Berlin, to entertain the possibility that energy was not continuous after all. Let that thought rest with you as your breathing deepens and your thoughts grow slower and softer. The device you used to find this video, the light in the room around you, the warmth of the air, the silent signals moving through the network that carried these words to you, all of it is quantum mechanical. All of it descended from a catastrophe that turned out to be a gift. There is something worth pausing over here in the gentle stillness of this late hour. Something that goes beyond the technical details of standing waves and equipartition theorems and quantum hypotheses. It concerns the nature of scientific progress itself and the particular character of the moment when something that was assumed to be true turns out, under sufficient pressure, to be false. Rayleigh and Jeans did not make a mistake. They applied the best tools available. They were careful, they were rigorous, they were right in every step of their calculation given the assumptions they started with. The problem was not in the execution. The problem was in a foundational assumption that no one had thought to question because it had always worked. The assumption that energy was continuous, that a physical system could hold any amount of energy, varying smoothly and without restriction, was not a guess or a conjecture. It was something so fundamental to classical physics that it was barely even recognized as an assumption. It was simply how energy was thought to be. When Planck showed that relaxing this assumption, replacing the continuous energy of classical physics with the discrete, quantized energy of the new framework, fixed the ultraviolet catastrophe, he was not simply correcting a formula. He was revealing that the classical picture of energy was an approximation, accurate at large scales, but breaking down at the atomic level. The smooth, continuous world that classical physics described was real, but it was the large-scale average of something that was, at its foundation, made of discrete pieces. This is a pattern that recurs throughout the history of physics. The classical, macroscopic description is not wrong. It is the correct description at the scales relevant to everyday experience. But it is an emergent description, arising from the statistical averaging of a deeper, more granular reality. The ultraviolet catastrophe was the first moment when this deeper reality forced itself into view, when the granularity of the quantum became impossible to ignore because the classical prediction based on the smooth approximation gave an answer that was not just quantitatively wrong, but infinitely qualitatively wrong. Planck was honest enough, and rigorous enough, and courageous enough to follow the mathematics where it led, even when it led somewhere he did not want to go. He later wrote that what he did could be described as simply an act of desperation. By nature, he said, he was peacefully inclined and rejected all doubtful adventures. But he had been wrestling for 6 years with the problem of equilibrium between radiation and matter, and he knew the problem was of fundamental importance to physics. A theoretical interpretation had to be found at any cost, no matter how high. At any cost, no matter how high. The cost was the continuous energy of classical physics. The gain was the quantum and everything that followed from it. It is worth spending a moment with the mathematics of quantization itself, not in the way of a textbook, with all its formalism and notation and demanding precision, but in the way of a story, allowing the shape of the idea to come through without requiring you to follow every algebraic step. Because the mathematics here is not merely technical. It is, in a deep sense, telling you something about the nature of reality, and the story it tells is worth hearing even at a distance. In classical physics, when you wanted to calculate the average energy of something, a molecule in a gas, a vibrating string, an electromagnetic wave in a cavity, you used the Boltzmann distribution. This distribution told you the probability of finding the system in any particular energy state, and that probability depended on the energy in a specific way. States with higher energy were less probable, according to a simple exponential formula. The probability fell off exponentially as the energy increased. To find the average energy, you multiplied each possible energy value by its probability and summed up all the contributions. In classical physics, where the energy varied continuously, this sum was an integral, a continuous weighted average over all possible energy values from 0 to infinity. The result, for a harmonic oscillator, was simply kT. The average energy was independent of the frequency of the oscillator. Every oscillator, regardless of how fast it vibrated, had the same average energy in thermal equilibrium. Now introduce quantization. The energy can no longer take any value. It is restricted to a discrete ladder of allowed values, 0 hf, 2 hf, 3 hf, and so on. The sum over continuous energies becomes a sum over this discrete ladder. The mathematics of this discrete sum is different from the continuous integral. The exponential weighting still applies. Higher energy states are less probable, but now the energies are spaced in units of hf rather than varying continuously. At low frequencies, where hf is very small compared to kT, the rungs of the energy ladder are closely spaced compared to the available thermal energy. The system can be found on many different rungs, and the average energy is close to what the continuous calculation would give, approximately kT. The discreteness is too fine to matter, just as a very finely graduated ruler gives the same measurement as a continuous one for most practical purposes. At high frequencies, where hf is large compared to kT, the situation changes drastically. The first rung above 0, the state with energy hf, has a much higher energy than the typical thermal energy, kT. The Boltzmann factor for this state, the exponential probability weight, is very small. Because the energy hf is much larger than kT, the system is very likely to be found in the zero energy state and very unlikely to be found in any higher state. The average energy is therefore much smaller than kT, exponentially suppressed, in fact. The high-frequency modes are effectively frozen out, unable to be excited by the available thermal energy. This is the mechanism of the quantum cutoff, not a new force or a new interaction or a new particle, just the simple mathematical consequence of replacing a continuous energy with a discrete one. The high-frequency modes cannot hold energy in arbitrarily small amounts. They require a minimum payment of hf. If that minimum is large compared to kT, they go without. And in going without, they prevent the energy density from diverging at high frequencies. They prevent the catastrophe. The beauty of this is that it emerges automatically from the quantization hypothesis without any additional assumptions. You do not need to postulate a separate mechanism for suppressing the high-frequency modes. You just need to say that the energy is discrete, with spacing hf, and the rest follows from the mathematics of thermal equilibrium. The quantum cutoff is not added by hand, it is built into the structure of quantized energy. This is, in miniature, the character of good physical theory. The right framework does not merely explain the phenomena you are trying to explain. It explains them inevitably as necessary consequences of its basic assumptions without the need for additional ad hoc mechanisms. Planck's quantization explained the black-body spectrum. It also, as subsequent work showed, explained atomic spectra, the photoelectric effect, the stability of matter, the nature of chemical bonds, and a vast range of other phenomena that classical physics could not touch. The quantization hypothesis was not tailored to fit the black-body problem. It was a general truth about energy, and its consequences were general. The story of the ultraviolet catastrophe connects, in ways that are not always obvious, to some of the deepest questions in modern physics, questions that remain open today, more than a century after Planck's discovery, questions that the best minds in theoretical physics are still working to answer. One of those questions concerns the vacuum. In classical physics, the vacuum, empty space, the absence of matter and radiation was genuinely empty. It contained nothing, and its energy was zero. But in quantum mechanics, this simple picture fails. The uncertainty principle, one of the foundational results of quantum mechanics, states that the energy of a system over a sufficiently short time interval cannot be precisely defined. There is an irreducible uncertainty in energy at short timescales. This means that even in a vacuum, even in what we would classically call empty space, there are energy fluctuations. The vacuum is not empty. It is alive with quantum fluctuations, with virtual particles appearing and disappearing on timescales too short to be directly observed, but real enough to have measurable effects. This quantum vacuum energy, sometimes called zero-point energy, has a direct connection to the black body problem and to the ultraviolet catastrophe. If you try to calculate the total energy of the quantum vacuum by summing up the zero-point energy of every electromagnetic mode, every frequency, every direction, every polarization state, you get an infinite answer. The sum diverges. Not in the mild way that the Rayleigh-Jeans formula diverged, because each mode had too much energy, but in a subtler way, because even the ground state energy of each mode is finite, but the number of modes is infinite. This vacuum energy divergence is one of the most vexing problems in modern theoretical physics. It connects to the cosmological constant problem, the question of why the observed energy density of the universe, which manifests as the accelerated expansion driven by dark energy, is so much smaller than the naive quantum mechanical estimate of the vacuum energy. Discrepancy between the quantum mechanical prediction and the observed value is famously one of the largest discrepancies between theory and observation in the history of science, off by a factor that is difficult to even express in ordinary language. Resolving this discrepancy is one of the central challenges of contemporary theoretical physics, and it requires precisely the kind of reconciliation between quantum mechanics and gravity that has so far eluded the best efforts of the field. The ultraviolet catastrophe of the early 20th century was solved by Planck's quantization. The ultraviolet divergences of quantum field theory, the infinities that arise when you try to calculate quantum mechanical processes at arbitrarily short distances, were tamed through the development of renormalization theory in the 1940s and 50s, through the work of Richard Feynman, Julian Schwinger, Shinichiro Tominaga, and Freeman Dyson. Renormalization is a sophisticated mathematical framework for consistently handling these infinities, and it works. The resulting quantum field theories make predictions of extraordinary precision that are confirmed by experiment. But the cosmological constant problem, the quantum vacuum energy problem, remains unsolved. It may be the 21st century's version of the ultraviolet catastrophe, a prediction that is catastrophically wrong, demanding a conceptual revolution that we have not yet found. The story is not over. It has never been over. The door that Planck opened in 1900 leads not to a room, but to a corridor, and the corridor extends further than anyone standing at the door could see. As the night deepens and the story settles into its final passages, there is one more thing worth carrying into sleep, a thought about the nature of the world that quantum mechanics reveals and what it means to live inside that world. The quantum world is strange. This is not a popularization or an exaggeration. The people who understand it most deeply, the physicists who have spent their lives working with the mathematics of quantum mechanics, who have derived its predictions and tested them and found them confirmed to more decimal places than almost any other prediction in science, those people find it strange. Richard Feynman, one of the most gifted physicists of the 20th century, a man who contributed profoundly to the development of quantum electrodynamics, once said that he thought he could safely say that nobody understands quantum mechanics. Not that it is wrong, its predictions are spectacularly correct, but that what it describes, what it is telling us about the fundamental nature of reality is genuinely and deeply puzzling. Particles do not have definite positions and momenta at the same time. This is not a limitation of our measuring instruments. It is a fact about the world. The uncertainty principle is not an expression of our ignorance, but of the irreducible fuzziness of quantum reality. A photon traveling from a source to a detector does not travel along a single path. It travels along all possible paths simultaneously, in a superposition that is only resolved when a measurement is made. An electron in an atom does not orbit the nucleus in a definite trajectory. It exists in a probability cloud, a quantum state that specifies not where it is, but the probability of finding it in various locations if you were to look. These features of the quantum world are not intuitive. They are not things that our evolutionary history has equipped us to feel comfortable with. Our intuitions were shaped by the need to navigate a world of medium-sized objects moving at medium speeds, a world where quantum effects are completely negligible, where the probabilistic quantum reality is so thoroughly averaged over so many particles that it presents the smooth, continuous, deterministic face that classical physics describes. We evolved to understand that face, not the quantum reality behind it, and yet the quantum reality is there. Planck glimpsed it in the winter of 1900 in the mathematics of a hollow metal box. Einstein saw it in the photoelectric effect. Bohr traced it in the spectral lines of hydrogen. Heisenberg and Schrödinger and Dirac gave it its mathematical form. And experiment again and again and again in contexts ranging from the emission of radiation from hot objects to the tunneling of electrons through barriers to the entanglement of particles separated by large distances, has confirmed that the quantum description is correct. We live in a quantum universe. We are made of quantum particles. The atoms of our bodies obey quantum mechanical laws at every moment. The chemical reactions that allow our cells to function, the electrical signals that carry thoughts through our neurons, the photons of light that enter our eyes and trigger the cascade of chemistry that we call vision, all of it is quantum mechanical. The quantum is not a remote and abstract domain visited only by physicists in laboratories. It is the foundation of everything, present in every atom of every object in the universe, including you. What is strange is that it is so hidden. The quantum world does not announce itself to our senses. It does not make itself obvious. It is revealed only through careful experiment and precise mathematics, only when you push into scales of energy and distance where the discreteness of the quantum becomes impossible to ignore. Rest of the time, in the everyday world of cups of tea and falling apples and glowing fires, it hides behind the smooth and reassuring face of classical physics, which is not wrong but only an approximation, an average, a large-scale picture of something that is, at the foundation, made of quanta. Max Planck pulled back the curtain just a little on that December day in 1900, and the world has been different ever since. Let us return for a moment to the experimental curves. Not as abstract data points or entries in a table, but as something almost aesthetic, the shape of a deep truth about the universe made visible in a graph. The spectral radiance curve of a black body has a particular shape that is instantly recognizable once you have seen it. It begins at zero for very long wavelengths, rises steeply, reaches a peak, and then falls more gradually back towards zero at short wavelengths. The peak shifts leftward towards shorter wavelengths as the temperature increases. At low temperatures, the curve is flat and low, with most of its area in the infrared. At high temperatures, it is tall and steep, with the peak moving toward the visible and ultraviolet. This shape is everywhere in the universe. The light from the sun, analyzed by a spectrometer, follows a Planck curve corresponding to a temperature of about 5,700 Kelvin at the visible surface. The cosmic microwave background radiation, the afterglow of the Big Bang, the oldest light in the universe, released about 380,000 years after the beginning of time and now filling all of space, follows a Planck curve with extraordinary precision. corresponding to a temperature of 2.7 Kelvin, just barely above absolute zero. It is the most perfect blackbody spectrum ever measured, a smooth, universal curve written across the entire sky, carrying within it the story of the universe's earliest moments. Every star has a Planck curve. Every warm object in the universe, every planet, every moon, every asteroid, every cloud of gas radiates according to Planck's law. The infrared cameras used by astronomers to image cool objects in space, by rescue workers to detect body heat, by engineers to find thermal leaks in buildings, by scientists to study the warming of the Earth's surface, all of them are measuring Planck curves. The shape that Planck worked out in 1900 from the data on blackbody radiation is the shape of thermal radiation throughout the cosmos. There is something deeply satisfying about this universality. Planck's law does not apply only to hollow metal boxes in German physics laboratories. It applies to everything, everywhere, at all temperatures. The curve is the same, scaled by temperature, shifted by temperature, but always the same fundamental shape. It is a universal signature of the relationship between matter and electromagnetic radiation, a relationship that the universe maintains everywhere and at all times with perfect consistency. And embedded in that curve, in the position of its peak, in the height of its rise, in the steepness of its fall at short wavelengths, is Planck's constant, the fundamental quantum of action, the smallest chunk of energy at a given frequency, the number that sets the scale of the quantum world. It appears in every atom, in every photon, in every quantum mechanical process, anywhere in the universe. It is, along with the speed of light and the gravitational constant, one of the three fundamental constants that define the scale of physical phenomena. The three numbers that, taken together, determine the size of atoms, the brightness of stars, the mass of black holes, the temperature of the cosmic microwave background. Planck determined the value of his constant, h, from the experimental blackbody data. By fitting his theoretical curve to the measured data, he could extract the value of h that made the curves match. The value he obtained in 1900, using the experimental data available at the time, was remarkably close to the modern accepted value. He had, in effect, measured the fundamental quantum of action from the glow of a heated object. He had read, in the shape of that universal curve, one of the most fundamental numbers in the universe. That is perhaps the most remarkable thing of all, not just that Planck found the right formula, not just that he understood the physical principle behind it, but that the principle, once found, connected immediately and deeply to a constant that appeared everywhere, in every subsequent development of quantum physics, in every atom and every photon in the universe. He had not merely solved a technical problem, he had discovered a fundamental constant of nature. He had measured, for the first time, the granularity of the universe, the size of the smallest chunks into which energy could be divided. And that number, tiny as it is, has been confirmed by experiment after experiment in context after context for more than a century, always the same, always h, always Planck's constant, the fingerprint of the quantum world. Rest now in the knowledge that the universe is measured and known, at least in this respect. That the smallest unit of energy at a given frequency has a definite value, determined from the glow of a hot object more than a century ago by a peacefully inclined man who did not expect to make a discovery of this magnitude, but who was honest enough and rigorous enough and humble enough before the data to make it anyway. The history of physics is dotted with moments of enforced humility, moments when a framework that seemed complete and reliable revealed an edge, a limit, a place where it could no longer hold. The ultraviolet catastrophe was one of those moments, but it was not the last. In 1905, the same year Einstein published his photon hypothesis, he also published the special theory of relativity, another revolution born from a foundational contradiction, the contradiction between Newtonian mechanics and Maxwell's electromagnetism regarding the constancy of the speed of light. A decade later, he published the general theory of relativity, which replaced Newton's theory of gravity with a description of space-time curvature. Each of these revolutions followed the same pattern, a framework that worked beautifully in its domain, pushed into a new regime, reveals an inconsistency that demands a deeper and more general theory. The relationship between quantum mechanics and general relativity remains the great unresolved tension of contemporary physics. Both theories are extraordinarily well confirmed in their respective domains. Quantum mechanics describes the behavior of particles and fields at small scales and high energies with breathtaking precision. General relativity describes the behavior of matter and energy at large scales and strong gravitational fields with equal precision. But the two theories are mathematically incompatible. When you try to apply quantum mechanics to the gravitational field, when you try to quantize gravity the way that electromagnetism was quantized into photons, you get infinities that cannot be renormalized away. The mathematics breaks down. The theories, taken together and applied in the regime where both gravity and quantum mechanics are important, such as in the interior of black holes or in the very early universe near the Big Bang, give nonsensical answers. This incompatibility suggests, to many physicists, that both theories are themselves approximations, accurate in their respective domains, but ultimately derivable from a deeper and more comprehensive theory that has not yet been found. String theory and loop quantum gravity are two of the most developed attempts at such a theory, but neither has yet produced experimental predictions that distinguish it from existing theories and can be tested. The deeper theory remains elusive. Perhaps, when it is found, if it is found, it will require something as conceptually radical as Planck's energy quantization. Perhaps it will require abandoning an assumption so fundamental that it is currently invisible, something so deeply embedded in how physicists think about space and time and energy that it is not even recognized as an assumption. Perhaps the next great crisis in physics will look, in retrospect, like the ultraviolet catastrophe, a clear signal, from precise data or from theoretical inconsistency, that the current framework is telling us something is wrong, demanding a response that is not merely technical but conceptual, not merely a new calculation, but a new way of thinking. If so, there will be somewhere a physicist in the role that Planck played in 1900. A careful, patient, perhaps peacefully inclined person who has spent years wrestling with the problem, who did not seek a revolution but found one, who followed the mathematics into a place they did not expect to go and reported honestly what they found there. The history of physics gives us every reason to trust that this will happen, that the universe will continue to reveal its deeper nature to those who are willing to look carefully enough and honestly enough and patiently enough to see it. That is the deepest lesson of the ultraviolet catastrophe. Not that classical physics was wrong. It was right, magnificently right, in its domain. But that the universe is always deeper than our current description of it. That every theory is an approximation, accurate at the scales where it has been tested, and potentially failing at scales yet unexplored. And that the path to deeper understanding runs through the honest acknowledgement of failure, through the willingness to look at a prediction that is catastrophically wrong and say, with whatever combination of determination and desperation the moment demands, that a theoretical interpretation must be found at any cost, no matter how high. Planck paid the cost. The universe rewarded him with a truth more beautiful and more fundamental than anything he had expected to find. And that truth, that energy comes in quanta, that the world is grainy at its foundation, that Planck's constant is one of the three numbers that set the scale of physical reality, is still unfolding its consequences in laboratories and semiconductor factories and hospitals and data centers and physics departments across the world, more than a century after a hollow metal box first whispered it to those patient enough to listen. The night is deep around you now, and the story has come to its resting place. Somewhere in the universe, right now, a star is glowing. It is glowing because the nuclear reactions in its core are heating its outer layers to temperatures of thousands of degrees, and those heated layers are emitting electromagnetic radiation according to Planck's law, the smooth, beautiful curve that Planck derived in 1900 and that has been confirmed by every measurement made since. The spectrum of that starlight, should it reach a telescope on Earth and be carefully analyzed, would match Planck's formula precisely, just as the radiation from every black body at every temperature always does. Somewhere a piece of metal is glowing red in a forge, not because anything mysterious is happening, but because its atoms are vibrating with thermal energy and their electrons are making quantum transitions between energy levels, emitting photons whose frequencies are concentrated in the red region of the visible spectrum. The color of that glow tells you the temperature of the metal as precisely as any thermometer, if you know how to read it. Planck knew how to read it. The walls of the room around you are emitting radiation right now, infrared radiation, invisible to your eyes but real, carrying energy away from the warm surfaces into the cooler air. The spectrum of that infrared radiation follows Planck's law exactly, peaked at a wavelength corresponding to room temperature, far in the infrared, invisible but present. The universe is performing its quantum accounting all around you, dispensing electromagnetic energy in careful, discrete packets, never allowing the high-frequency modes to run away, never permitting the catastrophe that the classical formula so precisely predicted. There is something comforting in that. The universe has rules, stranger rules than Newton or Maxwell imagined, rules that Planck discovered by following the mathematics into a place he did not want to go, but rules that hold. They held 100 years ago, when Planck stood at the blackboard in Berlin and wrote his constant for the first time. They held last year. They are holding tonight, quietly and without effort, as they always do. Every photon that reaches your eyes carries energy HF. Every quantum transition in every atom in your body obeys the rules that Planck uncovered. The laser in every CD player and barcode scanner and fiber optic cable operates on principles that were invisible before Planck's act of desperation in the autumn and winter of 1900. The transistor in every computer and smartphone and digital device exists because the quantum mechanics that Planck initiated told engineers how electrons behave in crystalline solids. The entire digital world, every image, every word, every piece of music, every map and message and stored thought of the modern age rests, ultimately, on the foundation that a peacefully inclined German physicist laid when he allowed himself, reluctantly and heroically, to follow the truth wherever it led. The hollow metal box has been put away. The experimental curves have been explained. The catastrophe has been avoided. And the vast, strange, beautiful quantum world that the catastrophe revealed is humming along quietly all around you, doing what it has always done, following the rules that have always held. Let the story settle into silence now. Let the curves smooth themselves into the dark behind your eyes. Let the equations dissolve into the soft background noise of a universe doing its quiet work. You have traveled from the flourishing confidence of 19th century physics to the edge of the abyss, and across it into the quantum world, and you have done it lying still, breathing slowly, drifting. The catastrophe was a gift. The wrong answer was the door. And on the other side of that door was everything. The atom understood, the chemical bond explained, the transistor conceived, the laser lit, the digital world assembled from the instructions written in the language of a constant so small it cannot be felt, but so fundamental that nothing about matter and light can be understood without it. Rest now. The quantum world is watching over you. The photons are moving at the speed of light in every direction. The atoms are vibrating with their gentle thermal energy. The universe is exactly as strange as it needs to be and exactly as orderly, and it will continue to be both long after this night has passed into morning. Sleep well, good night, still drifting. Let the rain take over from here. Close your eyes and let it wash everything away.